Hello everybody, welcome to our video lecture on discrete mathematics. A big part of discrete mathematics is actually counting all kinds of things, all kinds of mathematical objects. And in today's lecture I want to start with this topic, which is called enumerative combinatorics, and we start with counting the basic mathematical objects we have defined in the last lectures, like sets, functions, and so on. So as a motivating example, suppose I have to plan which dinner to cook for the next 3 days, Saturday, Sunday, and Monday. And let's suppose my cooking abilities are a little bit limited, and these are the 5 dishes I can cook. I can cook Chinese food, Mexican food, German food, pizza, and pasta. So for example, something I could do is I could say, well, on Saturday I cook Mexican food, on Sunday I could cook German food, and on Monday I didn't make a pizza. Okay, that's a perfectly fine thing. What I could do, well, I could also be lazy and say, well, on Saturday I make pasta, on Sunday I make pasta, and on Monday I make pasta. Now that's probably a boring dinner plan, but for now this is actually allowed. So I have no restrictions, I just have to cook 1 dinner per evening. So now the question is, how many choices do we have? How many choices do I have to cook dinner for the next 3 days? And this is very easy. So on Saturday I have 5 choices, on Sunday I have 5 choices, and on Monday as well. If I multiply them together, I have 125 choices. All right, so what you basically just have proved is the following fact: the number of functions from the set Saturday, Sunday, Monday into the set Mexican, German, Chinese, pizza, pasta is 5 to the third, which is 125. And in general, if you have 2 sets, A, B, the number of functions from A to B is B to the A. So here's an application of this innocent fact. So you might remember we have defined the power set of a set 2 to the s to be the set of all subsets. And now we're asked the following question: how many subsets are there? So for example, this is a subset. This is also a subset. But the set itself is also a subset of itself. And of course, the empty set is also a subset. So how can you count the number of functions? Here is a little trick. For a subset, I define 1 sub x. This is the characteristic function. It's a function from S into the set 0, 1, defined as follows. 1 sub x of A is simply 1 if A is in the set X and it's 0 otherwise. And now you actually see that there is a one-to-one correspondence between characteristic functions and subsets. And therefore we see, well, the number of subsets, the size of the power set, is simply the number of functions from S into 0, 1, and by what we have just proved, we see that is 2 to the size of S. All right, so here's the proof again, written up in a nice way. You can look at it in more detail if you wish. Let's continue to part 2, counting injective functions. So as I have told you, there are no restrictions to cooking food for the next 3 days, but of course, maybe my wife is not happy with me cooking Mexican food twice, so she actually wants that I cook 3 different dishes over the next 3 days. So this is not good. What would be good, for example, would be something like this. Just now the rule is no food twice. So basically now we are looking for an injective function. So how many choices do we have now? Well, for Saturday I still have 5 choices, and no matter what I chose, I have 4 choices left for Sunday and 3 choices left for Monday, and together this gives 60. In mathematical terms, it means the number of injective functions. That's actually a typo here. It's not infective, it's injective. Okay, the number of injective functions from Saturday, Sunday, Monday into my 5-element set is just 5 times 4 times 3, which is 60. And in general, if you have two finite sets A and B, then the number of injective functions is this expression here. And this is so important that I want to introduce a notation for this. This is very useful, but it's not completely standard in mathematics. So b to the a with a little line under it, it's just defined to be b times b minus 1, b minus 2, and you continue until you get a factors. And this is pronounced b to the falling a. All right. So get used to this notation. It's actually quite useful in enumerative combinatorics. So we have proved the number of injective functions from A to B is B to the following A. All right, so in part 3 I want to count permutations. What's a permutation? So let's change the setup a little bit. I'm planning a 5-course dinner for one evening. So there is one evening and I want to cook all the food that I can cook. So there are these 5 choices, so I have to cook everything. But I'm not sure in which order I should serve. So for example, I could say the first course is Chinese, the second is German, and so on. Or I could choose a different order, or this, and so on. And actually, as you already see, there are lots of combinations I can do. There are lots of ways in which I can order this 5-element set. How many are there? So here's the thing. The only thing I have to decide is what is the first course, the second course, the third, the fourth, and the fifth. So basically what I have to do, I have to choose an injective function from this set into the set CG M pasta pizza. Right? And how many such functions are there? Well, 5 to the following 5, which is 5 times 4, 3, 2, 1, which is 120. So we've proved the following theorem. These elements can be ordered in 120 different ways. And in general, if you have a set of size n, then it can be ordered in that many ways. And this is also a very important formula in mathematics. So we again introduce a new notation. And we pronounce it n factorial. Okay, and if you haven't discovered it yet, I have discovered a typo. This is of course supposed to be n minus 2. All right, another thing to observe, the n factorial is simply the number of functions from a set, the number of injective functions from S to itself. And if such a function is injective and S is finite, then this function must be bijective. And a bijective function from a set to itself we also call a permutation. All right, so we are ready for the last part of today's lecture, counting subsets of a certain size. So the setup is here. I'm invited to a party and I have to bring 3 dishes. So I just have to select 3 of the dishes I can cook. So for example, these here, okay, or these 3, and so on. All right, so how many are there? Well, one way to solve it is again to say, well, I have the set 1, 2, 3. I have to select the first, the second, and the third dish to bring. So I have to find an injective function from this set into this set. For example, this. So now we could say, well, you know, the number of choices is maybe 5 to the following 3, because this is the number of functions from the left set into the right set. But now you might protest and say, well, it's not completely true, because if I draw this function, it's a different function, but it gives me the same set, like this, right? It's a different function, but it gives me the same set. So every set can be obtained by a lot of functions. By how many? Well, if you think about it, by 3 factorial many. So what is this? This is 5 times 4 times 3 divided by 3 times 2 times 1. This is 10. So I have 10 possibilities of selecting 3 dishes. So this is the following observation. And in general, if you have a finite set, then it has this many subsets of size k. And this is also very important, so I want to introduce a little bit of notation. So the first thing is S choose k. This is just the number, it's the set of subsets of S such that x has size exactly k. And then this expression here we pronounce it n choose k. We'll pronounce this S choose k. So we basically have proved that the size of S choose k is the size of S choose k. And this thing is very important. It has its own name. It's called a binomial coefficient. The binomial coefficient is arguably maybe the most important object in enumerative combinatorics, so we will see it a lot during the coming sections. All right, that's it for today. Thank you very much and see you next time.